All right, guys, let's look at question 8 of the November 2022 paper 1. Question 8 reads as follows. It says, the graph of y equals to the derivative of f of x equals mx squared plus nx plus k is drawn below. The graph passes through the points -1 is to 0, -1/3 is to 0, q 1 is to 0, and r with coordinates 0 and 1. And now the first question is asking us to determine the values of m, n, and k. Okay, so where does m, n, and k come from? Those are the variables that we were given in the equation of the inverse graph. Not the inverse, but the derivative function. Okay, we've got the derivative function. This is the function we're talking about. It's y is equal to the derivative, which is equal to mx squared plus nx plus k. So what we're basically trying to find here is the equation of a parabola with an x-intercept of -1/3 and another x-intercept of 1, and the y-intercept of 0 is to 1. Okay, cool. Now, what's the algorithm of finding the equation of a parabola that has got x-intercepts? We always go y is a into x take away x1 and then x take away x2. So we've got y is a into x take away a third. So one of the x-intercepts is -1/3. If you take away a negative, it's as good as adding a third. And then on the other one, it's going to be x minus 1, okay, because the other x-intercept is 1. So x1 and x2 are the x-intercepts. Now for y and x, for me to work out the value of a, I'm going to substitute the point that was given to us, and that point happens to be the coordinates of r with coordinates 0 and 1. So my x there is 0 and my y is 1. So I have 1 for y, and I have x's as zeros, okay? But everything else will stay exactly as it has been up until this far. Okay, cool. So this then makes our equation to be 1 is a into, I think, 1/3 multiplied by -1 is going to be -1/3. And then when you multiply both sides by -3 to get rid of that, your a value comes out as exactly -3. Now that means we can be able to figure out what the answer is going to be of this equation by subbing back the value of a in the original equation that we have created, which is obviously this line here. So I'll have y is -3 into, I have x added with a third, and then I have x take away 1. And if you simplify this by applying the distributive law, you end up with x squared. I think a third minus 1 is going to give you a middle term of -2/3x minus 1/3. And then eventually the derivative function comes out as just -3x squared plus 2x plus 1 as the final answer for this particular function of the derivative. I think you'll agree with me, from what we are currently sitting with, we can then claim that since they're looking for the values of m, the value of n, as well as the value of k, our final answer is going to be that m is -3, okay, n is 2, and k is just going to be equal to 1. All right, this is how you're just going to work out these things. Okay. No matter where you are, the equation of a function that is parabolic will always be the same, and this is how you're going to always find the equation of this graph if you've got two x-intercepts given. 8.2 says it is further given that f of x, the original graph now, is -x cubed plus x squared plus x plus 2. We want you to determine the coordinates of the turning points of f. Okay, we want to know the turning points of the original function. Now it's negative there, so it means it's going to be a set phase parabola. I mean, a set phase, the cubic obviously is going to be the one with a negative a value, so I'm expecting it to look something like that. So they want us to find these points here where the graph is turning. But we've got the equation of the parabola, and there's a relationship between a cubic and its derivative. The derivative here happens to be passing this way, okay? And I don't know if you guys are familiar with this, but you need to know that the turning point, the x-coordinate to the turning point, is the same as the x-intercept of the derivative graph. this x value here is the same as the x-intercept of the function, because if you think about it, at those points where the parabola is cutting the x-axis, that's where the derivative is 0. And the turning point, that's where the derivative is 0, because that's where the gradient of the cubic is actually equal to 0. Right? It's very important, because this is here is a derivative function, and the one at the top here is the original function. So the relationship between them is that the x-coordinates of the turning point of the cubic are actually the x-intercepts of the derivative. That's how we know that we can just copy the values from the ones we are given in the graph there, the original graph. We're given that the turning point indirectly will have to have a negative 1 over 3 x value, and another x value will have to be 1, because these are the x-intercepts of the parabola that was given to us, the original parabola that was given to us. You see this parabola here, all right? So if x is negative 1 over 3 on one x-intercept, another one is 1. That means I've got the x-coordinates, not the y, just the x-coordinates of the turning points of that graph. Okay, so let's go to it quickly. I want to figure out what the y-coordinates are going to be. So if I've got the axis, all I'm going to do is ask the graph, what is f of negative 1 over 3? And that's what you get when you substitute 1 over 3 for all those axes here. 1 over 3 here, negative 1 over 3 here, negative 1 over 3 here. And then you also have to add 2 at the end. And it turns out that when you do that, you're going to get y as 49 over 27. Okay, it comes out as 49 over 27 when you substitute. So that's the y-coordinate, 49 over 27. Which is sometimes some people can refer to as 1.81. Nothing wrong with saying the y-coordinate is 1.81 to 2 decimal places if you want to. And then what about when x is 1? I'm going to sub 1 in the cubic. Okay, when you sub 1 everywhere you see x, right? What do you get as the y-coordinate? Well, when you sub 1 there, you end up with the number 3, because you're going to have negative 1 in the first term. You're going to have plus 1 and plus 1 and plus 2. That's 4 minus 1, which gives you an answer of 3. This one you can work out without even using a calculator. So the other turning point will have an x value of 1 and a y value of 3. Okay, cool. So those are the coordinates of the turning point of f, or the stationary points, and sometimes they are referred to as. Okay, now the 8.2.2 question says we need to draw the graph of f, indicating on your graphs the coordinates of the turning point and the intercept with the axis if there's any. So what do we have? Well, we've got the function given to us as negative x cubed, okay? I think it's negative x cubed plus x squared, right? This is what we were given now, the original function, plus x and then plus 2 with the end. What do we know? We know that this graph is going to have a turning point in 2 places, okay? I don't have to repeat those, but we know it's at negative 1/3 and 49 over 27, and the other turning point is going to be at 1 and 3. So this is what we have, okay? Now, we don't need the point of inflection. We don't know what the x-intercept is. We can try and find that, but we can work out what the y-intercept is going to be. What is the y-intercept? Well, the y-intercept is the last number, which is 2. It's going to be at 0 to 2. It's easy to compute that. For y-intercept, you make x 0. You're going to have everything disappearing in that function, and 2 is going to be the surviving number. Okay, cool. So let me try and get a picture of this so that we can work out the x-intercepts quickly. Now, when you try to work out the x-intercept, something interesting happens here. Okay, something very interesting happens. So generally speaking, if you are interested in finding the x-intercepts, all right, you're going to use what we call the factor remainder theorem. So you look for a factor, a number that you can sub, okay, in your function that will make this graph to have 0, a value of 0. We're looking for a factor here, okay? So our factor, we look for it by subbing 1. If 1 does not give us 0, we try minus 1. If minus 1 does not give us 0, we try 2, minus 2, up until we get a number that will give us an answer of 0, which will imply that that is going to be where we're going to get our factor. So it turns out that when you sub negative 2, here, something interesting happens, okay? Let's see what happens when you sub negative 2. You're going to get an answer of 0, okay? Let's see quickly. I think I have negative outside, open bracket. I'm subbing negative 2. It's important for you to see this. I'm raising that to the power of 3, okay? And then I'm going to add in brackets another negative 2 here, which must be squared. And I'm going to add again another negative 2 here in brackets, and then at the end I must add 2. And what do you get? You're getting an answer of 12. That means that it's actually not the right value. We want a number that will give us an answer of 0. So let's go back and check if we subbed everything correctly. And if we copied the function correctly, it's negative x cubed plus x squared plus x, okay? Plus 2 at the end is our final value there. Okay, cool. Now, if I go back, I have subbed negative here. I've got negative of negative 2 cubed plus negative 2 squared, okay? And then I have plus negative 2, the last one, and then plus 2 at the end. I'm supposed to be getting a 0 here. It's not working. What about if I sub, let's backspace here a bit, backspace, backspace. What if I sub the plus 2 instead of a negative 2? What would happen then? If I sub back a positive 2, what will happen if I did that? Let's see, we're getting 0. Okay, bingo, we're going to get 0 when we sub the number 2. That's awesome. So that means that this graph will have a factor when x is 2, which means a root is x is equal to 2. That means we can get our factor from that. Very powerful. So when I sub plus 2, I'm getting 0, which is actually awesome to see. That means that since the answer is 0 for this, then we can claim that x minus 2 is a factor. Okay, now from here we have to apply ideas of factorizing this. So I don't know if you're good at those, but I think by looking at this, we're going to find that the function now is going to be f of x is equal to x minus 2, okay? And then we're going to have a cubic here, a quadratic here, which is going to be quadratic so that we can get back our cubic. I think we need negative x squared here, okay? And then, because we're going to get negative x cubed at the end, I don't know what the monkey term is going to be here. There's going to be a middle term here. But then we're going to have a constant at the end that will give us the value of 2 when we multiply. So we need right there at the end a negative 1, because negative 2 times negative 1 will give us the last number, which happens to be that 2. So to work out the middle term, okay, if you think about it, the first term times the first term is going to give us negative x cubed. The last term times the last term is going to give us positive 2. We need the middle term. So there's many ways of figuring that out. I prefer the technique that says monkeys eat apples plus bananas, okay? What is your A? Your A is negative 1 from the cubic, right? You can use any technique that you use to factorize your cubic function. The p-value is the number that we were substituting to find the factor. It's the root, which happens to be 2. And your b happens to be the coefficient of x squared, because your cubic is in the form ax cubed, okay, plus bx squared, and then plus cx, and then plus d. So I'm getting the a and the b from the cubic. My a is negative 1, my b is positive 2. The p-value is, p is positive 2 because I'm getting it from the factor, and my b is going to be 1. So I'm getting an answer of negative 1 times 2, which is negative 2 plus 1. It gives us a value of negative 1. So I can quickly say this is going to be x take away 2, and I'm sitting with negative x squared. And if I look at this, I will have negative x minus 1. Now, it turns out that when you try to solve for x, this has non-real solution, because we have to equate this to 0 to find the x-intercept. So this has a non-real solution, okay? Non-real solution, and I can prove it to you by calculating the discriminant of that. Remember, for you to be able to solve a quadratic, you can use the quadratic formula. And when you try and find the b squared minus 4ac part, you are not going to get a positive value, because the discriminant of what you're looking at here, if I try and figure out what the discriminant is going to be by computing b squared minus 4ac, I'm not going to get what the answer is going to be, okay? Very, very important for you to understand that. We're not going to get a solution from that part. So that means this graph only has a root at x equals to 2. That's the only x-intercept you're going to have here. So I'll have 2 and 0 as the only x-intercept that I have here. Okay, let me create space here so we can have our beautiful graph and see how it's going to look. And I was expecting this because if you think about it, you have a graph, okay, that's going to look like this, right? This graph must tend at negative 1 and 1.8, so it's turning here at negative 1 over 3, all right? And 1.8 is somewhere here. That's where 149 over 27 is. That's 1.8. So it's turning here it must also turn at 1 and 3. So at positive 1 is here, and y is 3 somewhere here at the top. So you want your graph to turn in those two places. It must also turn here, right? So how is it going to have 3 x-intercepts because it's a cubic? It's not going to do that. So what is going to happen instead is it will come this way, turn here, okay, cut somewhere here at 2, turn here, and come back to cut again here at the bottom at x is equals to 2. So the x-intercept here will be 2. The y-intercept here is also 2. We worked it out. The turning point is at 1 over 3 and 1.8, and the other one is at x is 1 and 3. So this is how the graph is going to look. Just cutting x at positive 2 and nothing else. So you can try and convince yourself that negative x squared minus x minus 1 will not give you a solution. It's giving you an unreal solution. That means the graph will only cut x at one place. Okay. So now the follow-up part says here, point E and W are 2 vertical points on the derivative graph and are on the horizontal line. H is a tangent to the derivative graph at E, and G is a tangent to the derivative graph at W. H and G intersect at point D. Okay, so now we're trying to find these 2 tangents that they're talking about. Apparently we're going to have 2 tangents, but these are tangents to the graph of the derivative, not the original function. Okay, it's very important for us to keep that in mind. Right. Now, for us to be able to find the answers to these questions, we need a picture of what is going on, because that statement is very interesting. So how does the picture look? Well, we've got the y-axis and the x-axis, of course. We've got our graph that they're talking about. So I'm just going to put my y-axis here. We were told that this is how the graph looks. Okay, this is the graph of the derivative. This is the one they're talking about in the question. Okay, the derivative graph was this parabola. We were given this in the opening statement. We know what's happening here. We know what's happening there. We know what's happening also at that point. Now they're saying to us here there are 2 tangents. There's a tangent H, which is a tangent to the graph at point E. There's a tangent G, which is the tangent at the point W. And these 2 will intersect at the point A and B. So I'll draw one in green. So here's the first tangent. I don't know where it's touching the circle, the graph. So somewhere here it's going to be tangential. And then there's going to be the blue one, which is going to be in the different direction. So this one is going to be the second one. Okay. So they're saying here, those are the 2 tangents, excuse my drawing. So they're saying here they're going to intersect at a point here where both those coordinates will be true to both graphs. So that's the coordinates of A and B. But then they told us here that if that's the point D, E is on the left, W is on the right, but those 2 lie on the same horizontal plane. So they're basically on the same level, which means they're parallel. The line EW would be parallel to the x-axis. Okay, they lie on the same plane. That's what this part says here. Same horizontal line. Right, now we want to write down the value of A. They say write down the value of A. So the value of A, that's the x coordinate of the point where they meet each other. Now I don't know about you, if these 2 points are on either side of the parabola, obviously A will have a value exactly along the line of symmetry here. Exactly along the line of symmetry. Okay, so that line of symmetry is going to be the line at which A lies on. So in order to work out that coordinate, what I'm simply going to do is acknowledge the fact that if I know on the left-hand side I'm sitting with negative 1 over 3 and I have 1 on the right-hand side, I'm just going to work out the average, because the axis of symmetry is calculated by the average of that. Alternatively, I can just use the x coordinate at the turning point of the parabola, because we have the equation of the parabola. We worked it out. Okay, we did work out the equation of the parabola. What did we work out the equation of the parabola as? We said the equation of the parabola is, I think it was positive and not negative. Let's go back up and find that equation quickly. So that equation, we worked it out as, oh, there it is. We worked it out as negative 3x squared plus 2x plus 1. Okay, negative 3x squared plus 2x plus 1. Okay, negative 2x squared, negative 3x squared plus 2x plus 1. So I'm just going to work out the turning point x coordinate, or the axis of symmetry, which is negative b over 2a. That is negative of 2 divided by 2 times negative 3. And I'm getting an x value of negative 2 over negative 6, which is just going to give you a third. So that's the answer that I'm getting here as the value of a in this question. Right. And then the last question here says we need to determine the value or the values of b and G, where G will no longer be a tangent to the graph. So we want some number B, the y coordinate of that particular point where these two things meet each other, where those lines will no longer be tangents. And it happens obviously by if you look at it by inspection, you can clearly see that that's going to happen when B is smaller than 4/3. Very, very simple to see this. I hope you guys understand how to now work with questions that involve the derivative function and not the original graph of the cubic. So that the relationship between the cubic graph and its derivative is a very powerful one that we need to know how to analyze.